Welcome to the Mentored Engineer. In this video, we're going to learn something about rollers. Okay, so rollers are really cool. All right, rollers are like this one. That's just a cam follower or a yoke style roller, and cam follower is a roller bearing. You can get them sealed and unsealed, and they have a shaft coming out of the side. I can draw one for you here, but here's the roller part, and then it's got a shaft come out, and it'll spin on a roller bearing right there, and you can mount this shaft into whatever apparatus that you like. A yoke style one is kind of the same thing, but it's got a hole in the middle, and you can run a pin right through it, and it just spins right there. So that's all that is, cam follower, cam yoke. But these things are great for just rolling systems. If you've got something that rides on a series of rails, you're going to want to use something like this. Okay, so the first thing we're going to need to know is what happens at the contact where the two meet. How do we determine how much force is there? Because I'm sure we've all seen things that, it's a system like this and we overload it, and now it's got a little divot. So every time we run over it, it's just got a little divot, and that's not fun. It's as it goes across, and we know we overloaded it. So we want to make sure that we don't do this. We don't want that divot. We want that sound as it goes across. It's not good for the bearing. It's not good for anything. It's annoying, and all the other rest of that stuff. Okay, so what we need to look at is the Hertzian stress, or it's sometimes called just the contact stress. And this is the stress that we see if we were to do some FEA on this and actually do it. We would find out that the bottom of the thing actually squishes a little bit, and we'd end up with a big red, like almost balloon-shaped thing right here, and we'd see the same thing down here. All right, and that's just the two things mashing against each other, and we can calculate that. That is calculated here. Welcome back. Hey, we're going to talk about calculating the Hertzian stress of a cylinder on a flat plate, but our calculations require two cylinders to be used. All right, so how do we adapt between the two? And the answer is simple. We can use an infinite radius cylinder for our second one, and this will basically make it a flat plate. All right, so I've chosen a mile for the second one. That's pretty big, you know, when we compare this flat surface here to that. All right, so let's run through some numbers here. So let's look at an example here. I'm going to just come up with some random numbers. I'm going to say I have a force of 10,000 pounds. I have a width of my bearing, that's 4 inches. I have a diameter of the small bearing of 9 inches. And I have my flat plate has an infinite radius, which I said was a mile, 5,280 feet. My material for both things are steel, and it doesn't matter what the hardness of the steel, it's just the properties of the steel. But the harder the steel is, the better yield strength will be. Okay, so each member is 29,000 KSI and a Poisson ratio of 0.3, and that's just what steel is. So I can use these two equations right here to find out what my contact stress is, and in this case it is 53,000 KSI. All right, so the first thing I'm going to want to do is make sure that this thing does not dent the surface. So I've got two criteria that I'm going to want to compare my results to. The first is I don't want this yielding my section, okay? So I have to include other stresses that may be. If this is a track roller on a beam and the beam is, bending here, I've got a force this way, and then I've got tensile or compression stress going this way. So I got to add those two vectorially using the square root of the sum of the squares. All right, so in this example, I have used my principal stress that I've already calculated at 20 KSI. All right, and I'm going to use the square root of the sum of the squares to come up with a new stress of 56,728. And I basically want to make sure that this does not dent my beam. All right. You can add a more stringent design factor on there if you have more unknowns, like is there going to be impact loads or something like that. But I at least need to have this be greater than 1 so that it does not dent the surface. All right. So I got 1.06. Perfect. The other thing I need to look out for is the normal principal load, at least a 3-to-1 or whatever my design factor is for this principal load here. So that would be your 60 KSI divided by 20 KSI. Is that at least what I need my design factor to be? And in this case, it's exactly that. All right, so that is how you would calculate that and evaluate that for use in your application. Now, as I mentioned before, I just want to reiterate, using a harder material will allow the tensile strength of that material or the yield strength of that material to go up. So that's why harder materials are beneficial in our application. All right, now let's get back to applying these rollers. So now that we've seen the calculation, we can assume a couple things. And the first is that a hard surface will give us the best results for what we need to do. Okay, so the bearing itself usually is a hardened outer shell. They do that so it is not the first thing that wears. They're going to wear out your rail or whatever thing it's going to run over. All right. Also, we know that as we increase width, the stress will decrease linearly. But as far as how the diameter goes with our contact stress and area, a little bit more wishy-washy. It depends on what materials we're using and other surface hardness of that joint. Okay, so a quick and easy way to get your surface hardness up is to use some sort of hardened steel. Now, this can be some sort of tool steel that gets hardened, but there also is SSAB makes a couple different products. One of them is Hardox, and it's a very hard steel that is still readily weldable, and you can put in your design, so maybe a 1/4 to a 1/2 inch plate right there can increase your stiffness, and then you can have another mild steel 30 grade or A36 or similar grade behind it that would actually take a lot of the load, but you got a nice hard surface, so that'll get your bearing size down. Now, once you figure out what your allowable stress is, using the calculation we just shown you, you'll figure out what diameter is that you will shoot for. So let's just say that we've come up with our allowable stress allows us to have a 16-inch diameter track roller. Now, this is gigantic. It's 16 inches. It's going to be big. So we don't really want to have something that big. So how do we get this to be smaller? And this is the focus of what I want to show you right now. Is to maintain the same contact stress. If we add rollers, we divide the force by the number of rollers we have. If we divide this diameter by the number of rollers, we get the same contact stress in our equation. So if I have 2 rollers, I can go down to 8 inches. If I have 4 rollers, I can go down to 4 inches. Well, that starts looking more attractive. I want to show you how to do each of those so that you get the most bang for your buck. All right, so let's start off with 2. All right, if I have 2 rollers here, I can design in something called a walking beam, where it will essentially look like this. They come in a lot of different shapes and sizes, but a lot of them are banana shaped for a couple reasons. One, it kind of helps with the bending stress as it would go up, but it also gives you a lot of clearance, so you can put your mounting shaft, which is this one, This would be essentially the same location where we mount that. And we want to make sure that our force is distributed. So we would want this to be F over 2 on both sides. All right. Now, if this is mounted off center between the two, we would get different forces on each one because our statics has to work up because there's no place for this to build moment. All right, so if we call this entire distance L, so this would be L over 2. And this one would have to be, L over 2. All right, that way we sub moments on both sides and we get F over 2, L over 2, and that should equal F over 2 times L over 2. All right, so anyway, we end up with FL over 4 on both sides. Woohoo! All right, so this will be equal. It won't rock, and it'll give equal forces on each side. All right, now let's take that one step further and go to 4. All right, so here 4. And one thing I didn't mention before was the distance between the walking links doesn't have to be any set number. All right, you can have them, where the rollers are like, thousandth of an inch apart and they're barely not scraping each other as they're going up and down the thing. I recommend, quarter to half inch minimum, but they could also be 40 to 50 inches apart if you wanted. And that would just distribute the load on this beam a little bit better. Okay, so here's what we do. We have 2 of those sets that we just designed, but we'd also have another beam here with a pivot. Now, as we imagine here, we're going to have F over 4 on each one. And that's going to hold steady for all 4. We already know that these, if they have equal distance, we can do that. The same thing would be true here, is we would need this to be equal distance from this one, and everything will be fine. So it's just a bigger case of what we just did before with the 2 rollers. All right, so we went from 1 walking beam for 2, and now we have 3 for 4. Let's move on to 3. 3 is obviously going to be more complicated. So 3 rollers. We're going to start off with our F over 3, 1/3 of the load on each. All right, and logically, let's just start off with, we'll put 2 of these on a walking beam. All right, and as long as they're equal, who cares? All right, so we need a walking beam between this one and that one. So let's go ahead and make that here. Now this will obviously be a different shaped walking beam from the ones we've had before. But we need to put our bearing somewhere. So I drew it over here. I know it's wrong. You probably know it's wrong, but you probably can't explain why it's wrong yet, and that's okay. All right, so if I look at this distance, and I look at this distance here, we need to make that work out so that the moment on each side is the same. All right, so what we are going to say is we have 2/3 of the load here and 1/3 of the load here pushing up there. All right, so we've got on this side, our moment is equal to 2F over 3 times the distance. And our moment on this side, we'll call this DL for distance left. And then we've got F over 3 times D right. And we need to make sure that these 2 are the same. And basically, we're going to do that. So 2F over 3 times DL equals F over 3 dr. And let's just solve for DL. So DL got to be equal to F over 3 dr times the inverse of that, so that's 3 over 2F. And the 3's cancel and the F's cancel, so we get D left equals D right over 2. All right. So we'll just say this is dr and this is dr over 2. All right, so this is going to be half as long as this one. And that should make sense. Just follow the statics here and you get to the same answer. Okay, so after you get to 3 or 4 rollers, there's kind of no point to go to 5. It gets really complex and you probably have some other issues with your design, maybe you're using very soft materials. You probably get some other variables that you could look at to get it down to 4, 3, or 2 rollers. Well, this is the basics of rollers and how to get the most out of your roller system. Thank you for watching and have a wonderful day.